Yeah, last time we had proved that determinant of AB is determinant of BA. Oh, sorry, not this. So one immediate corollary is the following. A is invertible if and only if that A is not equal to 0. So if A is invertible, by definition, there exists B such that by the way, here there's a nice question. I think I'd asked you this earlier on in the course. You can try to prove it. That it's enough to, I mean, if AB is identity, it will follow that BA is identity as well. So try to prove that. You can't prove this just by trying to manipulate multiplying both sides by the way, don't try, if you want to do this problem, don't say that B equals A inverse or something like that. There is no meaning to that statement. Okay, the inverse, the concept of inverse comes in only when you have this both equations hold. But that's precisely what one is trying to prove in this problem. That one equation holds implies the other equation holds. Then you say that B is denoted by A inverse. But if you just start with one equation and then say multiply both sides by A inverse or something like that, it doesn't make sense. So anyway, this is not relevant to the main discussion, but you can try to prove this. And the nice thing about this problem is that I like to give this problem because if you think in terms of matrices, it is not at all obvious why this is true. But if you think of A and B as linear transformations, then proof opens up. Just by some general considerations, you can argue that this is also true. So anyway, I leave it to you to think about it. And don't use determinants for this problem. It's not relevant for this. So, but here in our corollary, what we are saying is that if A is invertible, then det is non-zero. Therefore, det AB is 1. So this product is 1. So both of them are non-zero. Now, what about the converse? Conversely, if, well, for the converse, what one can try to prove it this way. See, the statement, the converse would be the statement that if det A is not equal to 0, then A is invertible. So, well, or equivalently, negate this, take the contrapositive of this. If A is not invertible, then one would like to show that A is 0. Now, if A is not invertible, so if A is not invertible means that A not invertible implies that if you look at this AE1, AEN, these are just the column. From the linear transformation point of view, it's A acting on E1, etc. From the matrix point of view, AE1 is just the column vector X1. This is the column vector Xn of the matrix A. Well, if A is not invertible, what can we say about this set of n vector?
Linearly dependent.
Yeah, this is linearly dependent. Why? Well, if these vectors are linearly independent, then it will follow that A is 1-to-1, right? There's no kernel, or the null space is just the trivial space 0. But since A is from Rn to Rn, it will also follow that A is on 2. So A would be bijective. So it would have an inverse. So B, so AB equal to BA equal to I would follow. So that's a logic. So we conclude that this is linearly dependent. So basically, so I have C1 AE1 plus Cn AEN equal to 0 for some Ci in R, not all 0. Not all 0. Right. So just take the something which is not 0. Suppose Ck is not equal to 0. Then you just write that AEK would be minus Ck inverse So just write it as a linear combinations of the others. And then, well, okay, so basically, or in terms of the column vectors, I can write it as dxn. So this thing, well, you know what I mean. This the the kth entry is not there. So therefore, det A would regarded as a function of these column vectors would be det x1, and instead of xk, I just plug in the others. So summation di xi I not equal to k. Yeah, actually, the summation notation, sigma notation is very useful for writing stuff like this, where you want to omit one index. Here, if I want to write it like this, it's a bit awkward in the expanded form, but in this notation, I just put the index not equal to k. And then, well, now it's obvious because, so using the multilinearity property, I can write it as I not equal to k, determinant, and then the di comes out, x1, xi, xn. And each of these terms is 0 because the same xi will occur somewhere else also in the for every entry. So that proves that. Okay, so now let's move on. Now let's return back to let's return back to this thing, the derivative setting where this place where we had to invoke. If f from e to Rn is differentiable at P in E, then the Jacobian sometimes also it's also called the Jacobian determinant of f at P is JF P is defined to be determinant of f prime P. This terminology Jacobian is a bit confusing because some texts when use the term Jacobian to denote the full linear transformation, not just the determinant. That's why the safer thing is to say Jacobian determinant. But Rudin uses Jacobian just to mean just the determinant of f prime. Now, so whatever we have proved will tell us that JFP is not equal to 0. The single number detects if and only if f prime P is invertible. So this is the hypothesis. F prime P being invertible is one of the hypotheses in the inverse function theorem. So let's go back to the change of variable formula. For that, as I said, the key thing is this change of variable t. So t is from E to Rn. T is 1 to 1, C1, and we assume that T prime X is invertible. Now we know it's the same thing as saying the Jacobian is non-zero for all X in E. Okay, so the idea is that, as I told you, to write down this such a T in terms of as a composition of somewhat simpler functions. and then prove the theorem, the change of variable formula for all the simpler functions, and then prove that if the change of variable formula holds for the simpler functions, it holds for their composition as well. And so we'll end up proving it for any such t. Now, the point is, what simpler functions do we have in mind? So here, Rudin talks about what he calls primitive mappings. So it's somewhat like prime decomposition of an integer. So these are the analog of prime numbers. So these are functions which are essentially, it's the next best thing to identity from one point of view, namely it is identity in all the coordinates. No, not quite that. It's see, a function from e to Rn will have n components. So it will be like identity in on n minus 1 components. In one component, it's something, it can be, we are allowed to. So g of x is of this form. G of x is x1, xm minus 1. And in the mth component, I make it small g of x. Then again, I'm back to the identity components for some C1 function, small g. Now, the small g is real valued. Another way of writing this is in terms of the basis vectors. It is summation xi ei I not equal to m plus g of x times em. Or I can make it, I can also write it as g of x is x plus. Now, when I write it as all of x, so here in the first sum, I've excluded I not equal to m, but here the mth component will also be there. So I should subtract that. So it's g of x minus xm times em. So you can, but yeah, right. These are the forms that these two are the forms we'll work with, but keep in mind that g of x is just this kind of function. What I started with, g of x, here, small g of x, xm plus 1, and then xn. Right. So, now this primitive functions, well, when I said I want to break it up into simpler functions, these primitive functions are one class of simple functions. The other one is flips. Flip is a linear operator. Remember, operator just means linear transformation, where the domain vector space and the target vector space are the same. Linear operator on Rn, which interchanges two elements of the standard basis and keeps and fixes the other elements. So, in other words, the flip is of this form: B of E B of E1 equal to E1, etc. And then B of EI equals EJ. So let's say I is less than J. B of EJ equal to EI. B of EN equal to EN. So from the combinatorics point of view, this is just a transposition. If you think of permutations, this is just a transposition on the set 1 to n. Whenever you have a transposition, you can define a flip, and whenever you have a flip, you can get a corresponding transposition. So this is defined on the basis like on the standard basis like this, and then you extend it linearly. So that is a flip. Okay, so here's an example. B from R4 to R4. B of E2 equals E4. B of E4 equals E2. And the others remain wherever they are. B of E1 equals E1, B of E3 equals E3. So then what B does is B of X1 E1 plus X4 E4 is X1 E1 plus, well, X2 E4 plus X3 E3 plus X4 E2, which I can write as, I'll just bring the X4 E2 here, X3 E3. So the point of writing it like this, as Rudin remarks, you can think of a transpose of a flip as just sort of changing the coordinates of two of the vectors. See, for E2, initially the coordinate was X2, but now it has become X4. And likewise for E4. Okay, so basically that's it. Right. So now here's the theorem we want to prove. This is the main theorem actually. In the once we have this, the change of variable formula is not that difficult to prove. But to prove this is the main part. It's a difficult. It's not so obvious. But whenever you have let f from E to Rn be 1 to 1, C1 and f prime x is not equal to 0, is invertible for all x in E, then there is a neighborhood of 0 Oh, here I have to assume that zero is in E. This is not really, I mean, you can, even if you don't assume this, you will get a corresponding statement. It will be slightly more complicated. This is not the main part. It will just make things look nicer. Zero in E. And then you have this, then there's a neighborhood. The other important thing is this writing down every such function as a product of simpler functions cannot be done on the whole open set. It's only on the neighborhood of a point that one can hope to do this. Now, that will create a bit of a problem in the change of variable formula, because after all, the integration is being done on the full set E there, actually whole of Rn. So in order to deal with this issue that only in a neighborhood we can write like this, we'll have to introduce another technical notion, which is very important actually. This primitive mapping stuff you will never see again. But that other stuff that we are going to talk about next is something that you will see again and again in your studies in analysis or geometry. So that other stuff, the other technical device which we'll use has to be takes care of this problem that this whatever we are going to do is going to work only in the neighborhood of a point. So in a neighborhood of zero, we can write f as a product of actually, let me give this neighborhood U. By the way, I've been using the word neighborhood. Neighborhood just means an open set containing a point. Neighborhood of zero, of course, this neighborhood, this is contained in the original open set E, where I can write this as B1 composed with B n minus 1, then G1 composed with Gn all the way up to G1 of x for all x in U, where B1 etc. are flips and G1 etc. are primitive. I'm not specifying these, by the way, flips are linear transformations, so they're defined on all of Rn. But these primitive mappings are defined only on certain neighborhoods. So at each, for example, the first one, G1, will be defined on U, but the second one, G2, will have to be defined on an open set containing the image of G1, etc. So the domains of these GIs will keep changing. And what else? GI, yeah, and where GI are primitive, we can GI 0 equal to 0. GI prime 0 is invertible. This statement that GI prime 0 is invertible anyway, it's easy to see because from the chain rule, the derivative of f at 0 will be a product of various derivatives. And since GI 0 is 0, the chain rule, when we apply the chain rule, we'll get Gn prime at 0, Gn minus 1 prime 0, etc. So since f prime is a product of these various linear transformations, each one will have to be invertible. And yeah, okay. So we are the flips. Oh, flips or identity. I should also allow for the fact that I may not have to do any flips at all. That's also possible. So this is the theorem we are aiming for, that every such function, one-to-one, C1, and invertible derivative at all points can be written as a product of n-1 flips and n primitive functions. So this requires some work. So let's start the proof. I don't know if I'll be able to finish it today. Let me see. So I'll have to introduce one more class of functions. Let P0, Pn be projections onto various subspaces of Rn. P0x is the just I defined to be 0 for all x. So each Pi is a function, is a linear transformation from Rn to Rn. And it's defined. So P mx is projection onto the Rm sitting inside Rn. So it will be just x1 E1 plus xm em. So basically, the image of Pm is just Rm sitting inside Rn, as I said. These are all x1, x2, xm. The other coordinates are 0. And of course, from this definition, Pnx is just the identity. Pnx equal to x for all x. Now, well, I need to do some. Yeah, okay, fine. Let's see. As we need stuff, I'll introduce that. So this is an inductive process to break down this f into these flips and primitive functions. So what we do is, let's start with let f equals f1. I'm going to define n, so this fn's, f1, f2, etc. And each time I'm going to break it up, the original f, sort of chip away at the original f and get more and more parts to be flips and primitive mappings. Of course, what do I mean by more and more of f? So here's what I mean. For I, for 1 less than or equal to m less than or equal to n minus 1, assume the following. Vm is a neighborhood of zero. Fm is from Vm to Rn, C1, no, Rn is C1. So I assume that I already have Fm. The goal is to define Fm plus 1 in a certain way. Fm0 is 0 and Fm prime 0 is invertible. Well, this is not the final thing. So let me write 1, 2, 3, 4. The final thing is the main thing. These are all trivial things, whatever I've written here. The final thing says that you can ensure, see what we are, Pm minus 1 Fmx is Pm minus 1 x for all x in Vm. So what does this tell us? It just says that i.e. Fmx is of the form, if you look at the first m minus 1 coordinates, first m minus 1 component functions which make up Fm, it's just the standard ones for the identity. So this is x1, xm minus 1. The others we have no control over. So that is alpha, let's call it alpha mx, and then finally alpha nx. So this is what I mean by improving at each successive. See, what we are doing is we are going to right. So we start with F1. By the time we come to F2, F2 will be of this form. But actually, let me just see one thing. F2, Fm, how does it relate to the original function? Did I miss something here? No, that's fine. So yeah, that's okay. So we'll see how, I mean, even if we have this, it's not clear at this stage how, where the original function f is coming into picture. Of course, we have said that f equals f1. But if we, in this, ultimately, we are not interested in this fm, f1, f2, rather f2, f3, etc. We want a statement about f itself. So for that, we need to relate these fm's back to fm minus 1. And that way we can go back to f itself. So that we'll see how to relate. Yeah. Sorry?
Can you repeat that fifth point, sir?
The fifth point is just that it's an assumption. It's an inductive hypothesis. The assumption is that we are assuming that Fm, the first m minus 1 component functions of Fm, after all, what is Pm minus 1x? This is by definition x1, xm minus 1, zeros in all the other slots, right? It's a projection onto the m minus 1. So that means the first m minus 1 components of components of Fm are just x1, x2, xm minus 1. That's what I have here. This by definition is, if I write the component functions fm1 x, fm m minus 1 x, again zeros, right? So I'll be just picking out the m minus 1 components of fm. And those are just x1, x2, xm minus 1 is what this equation is saying. The other components of fm, we have no information. So I'll just call them some alpha 1. So these alpha i's are just some real valued functions, C1. Alpha I from Vm to R are some C1 functions. This is the hypothesis. So, I mean, if you start with, so I want to define, obviously I have Fm, I want to define Fm plus 1. So if you start with the very first one, m equals 1, then F. And so let's just, for clarity, let's see, m equals 1, F equals F1. To start the process, this should satisfy the hypothesis, right? Obviously, otherwise, that's a usual inductive step. Now, what would be V1? It's a neighborhood of 0, so I can just take to be, take V1 to be the full open set E. Then, oh, but did I assume that f of 0 is 0? Yeah, I did assume that. I don't know if I stated it here. Oh, no, I didn't state it. So I should say f of 0 is 0. So I need this. The original change of variable function satisfies f of 0 is 0. So then I'll get this gi 0 is 0, etc. So take V1 equals E. That takes care of the first part. And then F1 0 is 0. That's by hypothesis. F1 prime 0 is F prime 0 is invertible. Well, that is, we assumed it's invertible at every point, not just at 0. So this is also okay. This is okay. Then what about this one? Well, P m minus 1 would be P0. So this is 0. Is this true? Well, it's trivially true because I mean, P0x is supposed to be 0 for all x. So it's kind of satisfied in a very trivial way. So how do we, yeah. So in fact, let us just do it'll be perhaps clearer if instead of doing the mth stage, let me just do how to find F2. So let's focus on F2. So m equals, now I start m equals, so I started with m equals 1. So I want to now define F2. We define F2 as follows. Well, right. So since f1 prime 0 equals f prime 0 is invertible, then now let us, yeah, by the way, before I do this, perhaps I should say this. Let me just notice that since at the second step, the first step is kind of too trivial. We have not really done anything. So this alpha which occur here in this, all the alpha, every term will be alphas. There's no x1 up to xn minus 1. So f1x equals f of x. I won't keep on writing f of x. f1x is alpha 1x alpha nx. So I have the full set of component functions. I've not really improved anything. So let us try to get rid of this alpha 1 and make it x1. That would be the immediate goal. Now I'll say, since f1 prime 0 is invertible, well, there exists K such that D, so here M would be 1. Yeah, D1 alpha K at 0 is not equal to 0. Why is this? Well, yeah, so to see this, you just write, I mean, this equation, you just write it as f1x is basically alpha I x ei, and then f1 prime 0 is alpha I prime 0 f1 prime 0 acting on E1.
So what's D1 again?
This is just the notation for partial derivatives. dk.
Oh, okay.
dkf is del f by del xk. Right. So f1 prime 0 acting on E1. Now, what would this be? Well, D1 alpha I at 0 acting on multiplied by EI. This we have proved earlier. I mean, this is, I mean, when you write down, basically all I'm saying is that this is a fancy way of saying that if you look at the derivative matrix, after all, what is f1 prime 0 acting on E1? That is just the first column of the derivative matrix. And what is the first column? Well, you take all the component functions, differentiate them with respect to the first variable. And the corresponding column vector is the first column. And that column vector, I've just written it like this. Look, the point to observe is that I've differentiated with respect to the first variable. So it's just a more fancy, the usual interpretation of what the column vectors of a matrix are in the case of the derivative matrix. So I get this. Now the point is that since the matrix F1 prime 0 is invertible, yeah. Did someone say
Sir,
something?
previously, yes, sir. Previously, we have defined the Jacobian, sir. Is it related to this, sir?
Jacobian.
Previously, one definition we discussed today. That
No, that's a determinant.
Okay.
Yeah. So far, I'm not looking at the. I mean, the determinant as such has not played any role so far. In this whole theorem that I'm proving, the determinant will not play any role. The determinant will make an appearance again when we come to the change of variable formula. That was preparatory stuff actually.
Okay.
This formula actually, that primitive mapping stuff that we are proving now, it has nothing to do with, I mean, you can state it even before integration. You could have stated this formula right after the definition of derivatives. You don't need anything. You don't need to know what integral is. You don't need to know what the determinant is for this formula to work and so on. Okay. You just need to know, well, actually not, I mean, the formula can be stated right after the definition of determinant, but the proof involves one non-trivial theorem, the inverse function theorem. So the moment you have the inverse function theorem, I could have proved this. But if I proved it at that stage, it wouldn't make any sense whatsoever. What is so special about, why are we even proving this? That would be the question. Now, because the change of variable formula involves functions which are one-to-one and, well, essentially one-to-one and C1, change of coordinates, we have to consider stuff like this. We have to consider this theorem. But the content is actually, it's just linear algebra and some inverse function theorem. That's it. We don't even need determinants. Right. So in that sense, it's very elementary, but involved. Now, right. So where was I? Yeah. So I got right. The fact that this is invertible, F1 prime 0 is invertible means that, well, it has no kernel. So F1 prime 0 acting on any non-zero vector cannot be 0. So therefore, this thing here is not 0. I mean, that you can see from the matrix point of view as well. If a matrix is invertible, no column can be 0, right? I mean, a column cannot consist entirely of 0 entries. At least some entry in every column should be non-zero. That's all that I'm saying. So something here is non-zero in the sum. And that thing I'm calling as the D1 alpha K. That particular index is K. So we pick out that K. That's it. So D1 alpha K 0 is not equal to 0. What the idea is to move this K. Now that K might occur somewhere along the line. I want to move it to the first slot, first component function. So I do a flip. Let B1 be the flip. Oh, of course, I mean, if K is already 1, I don't have to do any flip. If K is not equal to 1, let B1 be the flip, interchanging E1 and EK. If K equals 1, then you just take B1 equals identity. Okay, so now here comes another important, the other part, the primitive mapping stuff. This is the flip part. So let G1 x be x plus alpha k x minus x1 and then e1. So in other words, what is this? This is just alpha k x and x2, all the others are the same. Okay, so so this is note that this is, of course, this is C1. G1 is C1. And it is primitive by definition. And what about its derivative? G1 prime 0. In fact, that was the whole point of choosing this condition. What is G1 prime 0? Well, if in terms of matrices, G1 prime 0, sometimes it's easier to just write down the matrix and see. So it is D1 alpha K 0. Now, what will the other entries be here in the first row? Remember that G1 is defined by this formula. So when I write down its derivative matrix, the first entry will be D1 alpha K0. Now, what about the other entries in the first row? Anyone?
D2 alpha K0, D3 alpha K0, so on.
Yeah, just all the other derivatives of alpha K at 0. Which are actually not, as it turns out, not relevant, but let's write it down. Dn alpha K is 0. Now, for the second one onwards, it will be just 1, 0, 0, 0, zeros, and like so on. So essentially, it's an upper triangular matrix with ones on all the diagonal entries except for the first one. So now the point is, as I said, we chose this alpha K so that this condition was satisfied. So when I calculate, if you want to see that the matrix is invertible, again, you don't need determinant, but if you take the determinant, you'll just get D1 alpha K0, which is non-zero. So the upshot is G1 prime 0 is invertible. Since D1 alpha K0 is not equal to 0. So let's see what the inverse function theorem tells us. By the inverse function theorem, there exists open U1 contained in V1. V1 I had just taken to be the original open set E. By the way, Rudin doesn't do this first step. I mean, he just jumps to the mth step. I thought I'll do this just to clarify things, but obviously I won't have time to do the general step as well. But if you understand this, you'll immediately understand the general step. There exists open U1 in V1. So this is V1 equals E. This is all our action is taking place in a neighborhood of 0. So this I call U1 now. And the inverse function theorem also gives me a V2 with a set V2 around 0. And this, the mapping being considered is my G1. So G1 from U1 to V2. V2 is, I mean, the inverse function theorem just gives some open set V. I'll call that as V2. That's going to be my next, for my next process, I'm going to use this V2. So G is 1-to-1, on-to, and C1. And moreover, G inverse from V2 to U1 is also C1. With all this in hand, let us define. See, the goal is, I mean, we want to get this F1, F2, etc., right? So I'm going to now define F2 Y oh, sorry. So this F2 is going to be defined on this one, V2. So F2 of Y is defined to be B1, the flip, composed with F1, composed with G1 inverse Y, where for Y in V2. So let's be clear about all the things involved here. See, this G1 is what I just defined now, which was, well, it's actually the formula is rather simple. So G1 is just this, alpha K, X2, etc. And F1, since I started at the very first step, F1 is just F itself. Obviously, this will not be the case when I proceed further. So F1 is F. And then the flip was, where did I define the flip? B1 is the flip interchanging E1 and EK. In terms of formulas, B1, X1, Xn will be just X1. Now, if I and J will be interchanged, Xj will come here, Xi will come here, and Xn. If I assume I less than J, these will get interchanged. So what you have to keep in mind in this formula is that this F term, here it's just F1, but in general it will be Fm, is something given in the inductive step. What are the new things being defined are this G1 and this flip. So using one flip and one primitive function, I'm defining the next function F2. Like this. Now, what is why do we do this? The idea is that ultimately it should remember what we want. We want to sort of chip away the original function and improve the goal. This is the goal to keep in mind is this one. Make more and more coordinates as just x1, x2, xm, while keeping the others as they are. So what we want from F2 hopefully is that at least the first coordinate should become the standard identity coordinate. F2 y1, y2, yn should be start off with y1 and the other stuff may be anything. So let me stop here. As I said, this is somewhat involved, but I need one more class. So on Wednesday, I'll show you how this works out, why this process will give what we want. So shall we stop here?
Yes, sir.
All right. Okay, fine. Thank you.
Sir, one small doubt.
Ah,